Hello, welcome. On this set of videos, we're going to go over section P.1, that's the probability section at the end of the chapter. And in these series of videos, we're going to go over the probabilities for equally likely outcomes. We're going to look at the complement rule, which is, we would read this notation as the probability that not event A happen, or the probability that event A does not happen. We'll look at the additive rule, which is the probability that event A or event B happens. And we'll talk about this or a little bit later. The conditional probability, the probability that event E happens, assuming event EA has already occurred. So conditional means something has already happened. And then what's the probability that something else will occur? We'll look at the multiplicative rule, the probability that events A and B happen, at the same time, that they both occur. And then finally, we'll look at two different types of special cases for events. What does it mean for two events to be independent of one another? And what does it mean for two events to be mutually exclusive or disjoint? All right, what do we mean by event? It's just something that happens or doesn't happen, something that's true or false. So it's a very open definition, very general. And look at some examples. If you're playing cards, poker, hearts or something, what's the probability that a randomly selected card that you get is a heart? That would be an event. Either it does or it doesn't happen. We'll talk about response variables more when we get to chapter 1. Say I randomly select someone in our class. What is the probability that the person is male? Or if you're wondering, what's the probability that it rains today when you get up in the morning? These are all just different events. And the probability of some event A, and event notation is P parentheses A, that kind of function notation, hopefully you should be used to from intermediate algebra class, is a long-run frequency, a proportion of times the event occurs. So probability is always between 0 and 1. Think of a percentage, but we convert this to decimal. So the probability of flipping a head and flipping a fair balanced coin would be 0.5. Probability always refers to some event. And if P of A equals 1, P parentheses A equals 1, that means the event A will definitely happen. And of course, if P of A is 0, that means event A will definitely not happen. Let's go through a couple examples. I'm going to go through these fairly quickly. Say we have the number of siblings. This is based on survey data I've done in previous courses. What's the probability y equals 1? This means what is the probability that a randomly selected person in the survey has exactly one sibling? About 48%. This came from a textbook, author's data, final grade in an elementary statistics course. Y is the final grade. So what is the probability that a randomly selected person got greater than 90% in the grade? 33.8%. Very high scoring class. Looking at World Data Bank data for college students in 2010, what is the probability that a randomly selected person, a college student, is female? Well, it's getting close to 60%, 58.5%. And lastly, looking at weather, I have not updated this, but probably if it rains today would be a 0.3 or whatever the weather app says. All right, so if all possible outcomes are equally likely, the probability of event is given by P parentheses A, the number of outcomes in A, the number of ways event A could happen, divided by the total number of outcomes. All right, this is kind of maybe a little bit hard to understand. So let's look at some examples. If we draw a card from a standard 52 card deck, it has diamonds, clubs, spades, and hearts, all the way from ace to king. The probability of picking a jack, there are 4 jacks in the deck, and there's 52 cards total, so it would be 4 out of 52, or 1 out of 13 reduced. Okay, so what we're going to look at mostly in this class, maybe not mostly, but a lot, is looking at contingency tables. So let's look at some demographics of sexual orientation of American adults according to a survey done in 2009, done by the National Survey of Sexual Health and Behavior. And we have this table, so we're going to have this table summarized. This right here is called a contingency table. It's kind of table given up of a bunch of data. And we have 2 different categories, male versus female, That's one variable. And then we have another variable would be sexual orientation, heterosexual, homosexual, bisexual, other. And then you don't have to include it, but generally you do want to include totals. So you total up all the male and female heterosexuals in this first row, and you get to the 4,673. So on down each row. 128 is 105 plus 23. 158 is 66 plus 92, and so on. And then if you add up all these totals, you get 5,042. So this is a pretty large survey done. I've given a reference down here from this paper. 5,042 people were surveyed. And then they do the same thing with the rows. Add up all of the males, all the females, and these should also add up to 5,042. And notice in their survey, we'll talk about this more in chapter 1, they got an exactly equal number of male versus female. But you don't necessarily have to get exactly equal, but that's a good distribution if you want your survey to reflect the actual population. Again, we'll talk about this more in chapter 1. Okay, so let's look at this contingency table on sexual orientation. And what would be the probability that an American adult, again, this is according to this data, is homosexual? I'll give you a couple minutes to think about this, see if you can get the right answer. Okay, so let's talk about this. We wanted the probability that an American adult. So we're thinking about all Americans, American adults in this. So our denominator is going to be the 5,042. We're going to use this sample to reflect all Americans, 5,042. And again, we're going to spend basically the entire semester talk about why we can do this, when we can do this, what type of error there is on these types of questions. But assuming this 5,042 surveyed represents all U.S. adults, the probability that someone's homosexual would be, in this survey, there's a total of 128 that said they're homosexual. And then so we're going to take that number divided by 5,042 to get 2.5% roughly, 0.025. Okay, so in the next video, we're going to continue looking at this table for a couple more questions, but we'll start looking at combining events.